Hi, everyone. Today we're continuing our conversation about investigating the relationship between two variables. On Monday, I posted a video walking through the process of cross-tabulation, which is a great way to investigate the relationship between two variables that are either ordinal level or nominal level data. And today we're going to talk about bivariate regression. This is also a great introduction to the concept of regression in general, which will be the focus of our lessons and quiz for next week. So first of all, I want to begin just by reviewing what I talked about on Monday about how we can describe the relationship between two variables. So we can speak to the direction of the relationship, the form of the relationship, and the strength of the relationship. And regression analysis is very intuitive because we can speak to all three of these together: the direction, the form. In this instance, we're going to talk about data that we expect to take a linear form, and also the strength of the relationship as well. And then as we move into multivariate regression, meaning regression that looks at multiple variables at once, we can also use regression to assess causality, because we can control for those spurious factors like we talked about in the very beginning of the semester. But we'll get more into that next week. So again, just another example. This was the same what I showed before, but thinking about the form of the relationship. In regression, the type that we're going to do today, called OLS, ordinary least squares regression, we assume that our data takes a linear form, the form of the line. So again, it's going to be talking about the relationship between the independent variable x and the dependent variable. So each of these dots would represent one of our units of analysis and where they would fall in relation to one particular independent variable and the dependent variable as well. So obviously, we can't expect our data to take this linear form unless these were ordinal or ratio level variables. So for those of you who have a dependent variable that's not ordinal or ratio, for your final papers, we'll talk about a different type of model that you can use next week. Okay, so again, what we're talking about today, we're continuing to talk about different measures of association that indicate how our variables are related. And again, of course, it's important to know our levels of measurement, like I just spoke about. And of course, it's going to also relate to your particular research question. So again, today in particular, what we're going to focus on is right here, this linear regression, speaking about looking at a dependent variable that's quantitative. And what they mean by that here is ordinal or ratio. So for those of you who have a dichotomous dependent variable, we would look to logistic regression instead, and I will explain more about that next week. One thing I do want to point out that when we're talking about regression, it's most important to look at the level of measurement of the dependent variable. We can include independent variables in our analysis that are categorical, so meaning just nominal level data as well. And I'm going to show you how we do that next week as well. Okay. So again, regression is a tool for describing how strongly, and under what conditions an independent variable and a dependent variable are associated. And again, it can be used to make causal inferences. This is the reason why you're seeing in the articles that we read for class, so many of them include a regression model because of the ability to use regression to make causal inferences. Okay, so the ordinary least squares regression model, commonly called OLS, formula is the formula of a line. So those of you who are math people familiar with geometry, what you'll see here is the formula describing the slope, describing the formula for a line. So our y, again, is our dependent variable. A is the y-intercept, or also called the constant. You might have seen this mentioned before in the regression tables. It reports the constant. So what's the value when the y and the y and the x lines intercept? And then B, our beta, is actually the slope of the line, is our beta coefficient that we've already been talking about. And then X is our independent variable. So this is our formula for a regression model. So some things we can see by looking at this formula is that if the beta, the slope, is positive, the relationship is positive. And if the beta is negative, the relationship is negative. So when you look into those tables to the beta coefficient, it tells you the direction of the relationship. And then, of course, you look at that direction and see if it fits with the proposed hypothesis. What's also intuitive about the beta is it doesn't just speak to the direction of the relationship, but as the slope indicates, it speaks to the size of the relationship as well. So how we interpret the beta coefficient is how much does the dependent variable change for each 1 unit change in X. So by I mean 1 unit, it's dependent on how that particular independent variable is measured. How much does the dependent variable change for that? And hopefully that will make more sense when we go through some examples. But I think at this point, it's just, it's important to note that the beta as the slope allows us to speak to both the direction of the relationship and the size of the relationship between the two variables. And then again, the constant is the value of the dependent variable when X equals 0. So again, when those lines intersect. So for many of our research questions, it's not always really valid to refer to what the constant is, but sometimes it might be. So what a regression model does, it provides the best fitting line by minimizing the squared distances from each data point to the line. So what does this mean? Minimizing the squared errors. Basically, in the beginning, when I showed you the data, it's what we call a scatter point, where we saw our different data points matched out. What the regression model does is basically draw a line amongst all your different data points and tries to minimize the distances between each data point in the line. So it draws the line that best fits the data. So of course, if your data is already looking very much like a shape of a tight line, suggesting a very strong relationship, those data points would be minimized. But as they're spread out, of course, you're going to have some points that are much further from your line, and that's going to kind of increase those squared distances. And again, this refers back to your standard errors as well. So how much distance is there between the separate data points and the line? Another coefficient we talk about in terms of regression is R. And this is the measure of both the strength and the direction of the linear correlation. So if we see a 1, that's going to be an R of 1 is a perfect positive association, and a negative 1 would be a perfect negative association. So again, speaking to the direction, whether it's positive or negative, and speaking to the strength as well. And then if you had an R coefficient of 0, that would mean no relationship between the independent and dependent variables. A very useful statistic that I'm going to be speaking about quite a bit is the R squared. This is the explained sum of squares divided by the total sum of squares. It's not important that you know how to calculate the R squared, but basically just to have an understanding that, again, this is showing how well the data fits that line. So again, those squared distances from the line. So R squared is a valuable statistic because it indicates, how well does your regression model fit your data. So speaking about saying that in a different way, how I like to think about it is how much of the variation in your dependent variable, how much of the differences that you see is explained by your independent variable. Okay, so hypothesis testing using regression. This should feel very familiar to you guys. This is actually what you did in quiz 2. And even though you guys expressed some hesitation, you guys did a really good job with quiz 2. So hopefully much of this feels like review. So again, our null hypothesis in a regression model is that beta, that slope, would equal 0, because that would show us kind of no relationship between the independent and dependent variables. In regression, we can have either the t distribution for small samples, less than 20, and the normal distribution, or the z distribution, for larger samples, those greater than 20. So again, for our quiz last week, the N was, I think, 1,051. So many of you guys did a good job identifying that would mean that we are dealing with the normal distribution. And then again, we want to look for a relationship that's significant at the 0.05 level. That's going to be that p-value of 0.05 or less. So how do we find whether the variable is statistically significant? We calculate the z-score for the normal distribution, or we calculate the t-score for the t distribution. But for both of those, we're looking at that beta, that slope coefficient, divided by the standard error. And most of you guys were able to identify that in the regression table. The key was just making sure that you were looking at the independent and dependent variables as specified in the hypothesis. So with the z-score, if we want the relationship to be statistically significant at the 0.05 level, we're looking for a z-score of over 1.96. And again, that's been derived by statisticians, and if you want to look at kind of how that works, that's what's found in the appendix A of your textbook. The t distribution is specified in appendix B of your textbook. And in order to find that critical value in the t distribution, you have to know the degrees of freedom, which is similar to what you saw with the chi-square distribution. So we take the n, the number of observations, minus 2. So again, because the t distribution is for small samples, the critical t is dependent on the sample size. So the smaller the sample size, the higher the t value you'll have to achieve to reach the level of statistical significance. And again, you can check that out. It's appendix B of your textbook. But for most of you, and with your own research projects, I encouraged you to hopefully at least have a sample size where we'd be dealing with the normal distribution. And for almost all the examples of articles we've been using in class, we've been seeing that normal distribution as well. And then the last step is going to be calculating the confidence interval. So again, when we have that beta coefficient, that size, it's surrounded by actually a confidence interval. So we would know that the true value is between something and something else. So in order to calculate the confidence interval, we take the beta coefficient, that observed beta, like from the table, and we would do plus or minus the critical t or z-score needed. So with the z example, that's that 1.96 times the standard error. So that is going to give us the range of possible options. So the slope is somewhere between blank and blank. And that ties back to our null hypothesis, because if we calculate the confidence interval and 0 falls within that interval, then obviously we can't have any confidence that there's any real relationship between our independent and dependent variables. So again, hopefully this feels a little bit familiar to you, this logic, and I'm going to keep repeating it as we walk through examples both this week and next week. And I will be walking through the examples from the article this week, Wednesday at 1 o'clock. Thank you for tuning in. Bye.